schema. With starting from sand, we can construct sandcastles, but we can construct also buildings. We have glass and fiber optics. This is the part in which we use silicon dioxide. So most of photonics is based on silicon dioxide. The other part is to produce silicon, starting again from sand, and we obtain silicon, and we know today what people done with all this. So electronics, mobile phone, photovoltaics, etc. So we construct a world based on, we can say, on sand. It's not only sand, but most of them. So we have two sciences, electronics and photonics, and these two sciences can have the same goal, to exploit solar energy. So, by these two ways, I present you. So first, the electronics contribute to solar energy conversion by silicon wafers, which were used at the beginning for electronics, and now in the first generation solar cells are very used for most of solar cell, commercial solar cells are based on silicon. Then we have the second generation solar cell based on thin film. Here again we have silicon, amorphous silicon. And also we have the third generation of solar cell, which are based on generally on organic materials. So I will speak just a little bit about third solar cells, third generation solar cells, because I work most in this field. So the trend in this part of research is to find new active materials, and also to replace ITO, which is a quite expensive material. So new electrodes are composed of 3 layers, so which could be replaced in very successfully ITO. It's by a layer of oxide thin film, metallic layer, and another layer of oxide films. The advantage of this 3 layer is electrical stability, and tomorrow I will present a talk concerning the advantage on these 3 layer electrodes comparing to single transparent conducting oxide. So this maybe will be the future for organic solar cells, to replace ITO with these 3 layer electrodes, which could be zinc oxide, a metallic layer, which could be silver or gold or other metals, and then zinc oxide again, or ITO or other oxide. So let's have a look on these two sciences, electronics and photonics, and if we look, we see there is a lot of similarity. We have cables, we have optical fibers. Here the carrier charge are electrons, here the information carrier are the photons. So if we look just like this, we can see there is some similarity between these two sciences. So we can imagine maybe that tomorrow we will have computer not using electrons but using photons. So how we can maybe pass from electronics informatics to photonics informatics. So today we have photonics, which didn't realize what electronics realized with computers, but maybe in the future will be possible to have a computer which uses photons. So today the principal materials are silicon dioxide and silicon, and tomorrow very promising materials are also plastics and graphene for both of these fields. So we can imagine to pass from electronic informatics to photonic informatics by 4 steps. So first we need to realize, to find the information carrier vector, to realize the circuits, realize the generators, and realize the transistor. These are the basic elements in electronics. Can we find the equivalence for these elements in photonics? This is the question. And by the research which is done actually, we can see that many of these steps are already done. And let's have a look. So for the equivalent for information carrier, in electronics we have electron. In photonics we can have photons, soliton, light bulb, or plasmons. For circuits and electronics, we have cables, which are generally metal, and in photonics, we can create waveguides, which are generally silica, multilayer metal, dielectric waveguides, or organic materials waveguides. For the generator, we have the classical generator, electrical, that you know, and for photonics, we can consider that generator are the lasers. We have transistors in electronics, and we will see that we can find the equivalent in transistor and photonics, or we will see later maybe in plasmonics, which are plasmostat and optical transistor. So we can imagine that we will have a new science emerging, which is plasmonics, which is already exists this science. So why plasmon is interesting? Because it's permitted to transmit information with higher frequency than existing today, and opens also the area of nanophotonics informatics. And have also a unique capacity to confining light in very small dimension. So if we start to see the 4 steps, so the first step was to find the particular, the information carrier. Let's suppose this one is a plasmon. And now we pass to the second step, which are cables. So we saw in electronics, for example, for solar cells, we have some electrodes, which are 3-layer electrodes, and we use these for plastic electronics or for plastic solar cells. And let's have a look on photonics. On photonics, we found recently optical waveguides which have the same structure, which means an insulating layer, a metallic layer, and another insulating layer. Oxides in film are general insulating, so it's quite the same structure. And now let's have another look on organic solar cell. The structure for organic solar cell, classical structure, is a substrate with ITO or transparent electrode. This is a buffer layer, and then we have a blend between a polymer and fullerene, and a buffer layer again, and then metallic layer as a back electrode. And if we look in this picture, which presents in photonics an organic waveguide, we will see the structure is very similar to the structure of an organic solar cell. So just we invert the structure and compare to the structure of organic waveguide in photonics. So we see very, very good correspondence and very much similarity. So we saw the particles, we saw the cables. Now let's have the circuits. So in electronics, everybody knows we have different circuits. How I can have circuits for using, for example, photons or plasmon. There are already some publications in which people have done optical circuits. So in the place to inject electron, we inject a photon which combine with the existing free electron, and we create plasmon, and we can create the same circuits or quite the same circuits existing in electronics, but by using photons. So these are some examples of article published in photonics. So other thing which remained is the generator. So we say that it's about lasers, which are generators in photonics. So today you use very often the sand. A material very promising for tomorrow will be maybe the graphene. And graphene is also used in photonics and electronics for different aims. So for electronics, it's very promising material for plastic electronic and plastic solar cell because it's very good conductor material, transparent, and it has a very good mechanical properties. For photonics, this graphene is very useful for a fiber laser to create an ultra-fast saturable absorption, which permitted to send pulses of light with very sharp peaks. So we see here is an example of how to transfer graphene films into plastic substrate. So this is already realized industrially, and the costs are diminishing than a few years ago. And the question what we can imagine is graphene nanoplastonics could be an emerging field, and we have a recent published in Nature Photonics in this year. So let's have a look at the last element for this comparison, which is the transistor. Maybe one of the most important elements in electronics is this transistor. Can we have the equivalence in photonics? So in transistor, organic transistor, if we have a look, this is the structure of an organic transistor. And let's have a look in first optical transistor, which was done in photonics. And we saw it's using also an organic molecule, which is very similar to pentasene molecule used in organic transistor. So there are, in the future, maybe other devices which are already have name, which are plasma cell switch, or optical, which is an optical switch. So what does that mean? So we have found maybe many equivalents between electronic and photonics, and maybe in the future we'll be able to create with photons what we create today with electrons. So the question which arises again is maybe did we need in the future the electricity? Why we need electricity? First, for our need is to heat, to have light, to use electricity for motors and informatics. And let's have a look what we can do with solar energy. So with solar energy we can produce light. If we find a way to storage the light, we can heat this is very easily, sun heat everywhere. And we have the other two problems of how we use the solar energy for informatics. So today we transform the solar energy in electricity. So we use photovoltaic panels, and we can use it for informatics and motors. But if the way of this part, if the research in the future, we realize all this way, by this at least 4 steps I present you before, that means that with this step is already done, so we can create informatics just by optical microcircuits. So it remains just one way how we can create photonic motors. So if we can create also motors using light, that means maybe in the future, far future, maybe we don't need it to pass by electricity. So the biggest challenge for tomorrow will be to realize photonics informatics by these different steps I presented you before. And for the motors, if we can go further, we can see that there are already groups and as well already prove that using light we can make motors. Here is very small example, and motors not so powerful like motors which use electricity, but that proved that it could work. So maybe many of you could know the Crookes radiometer. If not, I will explain you. And it's also a group in Great Britain which done optical manipulation using lasers. So here are some balls of polystyrene balls which are moved using lasers. So that means we can create motion by using light. So at the end, so what is this research aim? It's to conserve our world, and today we use these systems, and maybe tomorrow we will use other systems. So thank you very much for your attention. So I